Hey everybody, it is Friday. I might pull up some 320 here. If you're here, say hey. I don't know if we have anyone watching yet, but feel free to say hi and ask questions if you have them. We might have one person watching, or maybe that was me clicking it. But I'm going to pull up, I think, 320. So if you're here, you get to ask all the questions. And I'm watching Project 1 for 201 is almost all graded. That's excellent. Let's go ahead, and 320 has an assignment coming up next week. Next week, 320's assignment. Might take a look at that a little bit here. Let's go ahead, and I have it loading up right now. 2 seconds here. My R Studio is all crazy right now. Let me close down. There we go. Don't save. And we're almost there. Okay, it looks like we're good to go. I might take a look at some 320 here. Close out all this. There we go. Let's see if anyone's in the chat. No one's in the chat. No, that's all right. So we'll get started here with some 320. Let's take a look at some regression. Let's talk about this. Let's go over here. Okay, here we are. I feel like my lights are low. Sure, we'll do that. There we go. So with 320, this week we started up regression, which 201 might be like, wait a minute, they're doing regression? Yes, everyone's doing regression. We're all learning regression. So we have some of the problems are from the book. That's awesome. And we need to load up the EX3 NFL data sets. This is NFL data right here. And we're just going to take a look at some of the data. Now, I believe we look through. Let's go ahead and run this right here. Now you have to run library reg class because that loads the library, which the library just loads up a bunch of things we need. What is a library? Well, a library has in it functions, it has in it data. So you can see here I'm just looking through the library, and it also has a bunch of data packages too. So the library is basically like downloading a whole bunch of video games. So when you load it up, it loads up everything for you, but this is just a whole bunch of stuff that you get for free. And the data right here, we're gonna load up the data set, and that's basically loading in an Excel worksheet. So now we have our Excel worksheet basically, and we have data we can work with. And this is how you load data that has been preloaded into R. So it just depends. We have data like the sunspot data. These are all in data sets. You see student is in reg class. So if I were to not have reg class loaded up, student would not be available. Student is only available if you have reg class currently running because it's a data set inside of reg class. Like churn right there, leaving customers who are churning. That's also inside of reg class. Things like data set, US judge ratings, you can load that up right here. And now we've got that loaded up. The promise means it's actually there. Once you run it, for some reason, if you run something on it, it runs, but the promise means we promise it's there. I don't know why it does that. So we've got these, I'm trying to see which judges they are, if I know these judges, but I don't know those names. Someone's been like, how do you not know Shay? How do you not know Spunzo, Stapleton? I don't know them. I'm sorry, I don't know those judges. And I'm going to clear the global environment just to get rid of these things. Then we're going to load up the data set again. And now we just have the one data set loaded in. This button right here clears the global environment, just kind of cleans out this area. You've got cleaning buttons for every area. You can clean this out. You can clean this out. So you can just clean it up if you want. So what we're doing in this chapter is we're making linear models. And to make a linear model, we need to know how to run a linear model. And linear model is just LM. Now I'm going to use some of the variables here, like let's predict next year's wins. And so we've got to type it correctly. Next year's wins from this year's wins. I might not be doing random problems. So I'm just doing random problems right here. And hopefully no one thinks I'm doing this one right here. Just kind of loading up the data set, working with it, and showing how to do some linear models. You have to do data equals and data equals EX3 NFL. And let's show the format of this. So the format of this is, there we go, y tilde x comma data equals the data frame. And we are going to store it into an M, which is a model. Now, it doesn't matter what you call this. This is just where you're storing it. Store spot. So this is the spot you store it to. So you store it into something, and it's called y tilde x comma data equals. The y is the y variable, the one we want to understand. The x is the x variable doing the explaining. And the df is the data frame, which we are using where our data is inside of. There are instances where you don't need the data frame if your vectors are in the global environment, but our vectors are not in the global environment. What I mean by that is the following. I'll show an example of that. If you have a vector 1 through 10 right here, that vector is in the global environment. if you have a vector 1 through 10 right here, this vector is in the global environment. And our vectors are called y and x. So we can make the linear model right there because y and x exist in the global environment, and that's why that works. Now, if you don't have y and x in the global environment, you try to run this, it won't find y and x. Well, it first breaks on y and it says we can't find y and the code just stops. So this doesn't work unless you have those in the global environment and then it runs. So what we need to think about is if we didn't have on this ex3NFL, why this wouldn't work. It's because it's going to look to the global environment. Also, now I don't have the data frame loaded up. Now I do. And if we now run it with the data frame on the back side of it, then it will work because it's going to look inside of here to see the names of next year's wins and wins. So it's able to grab this variable here and this variable here because it's told look inside this data frame. And from here, we've got our model. We can summarize our model and we get our usual output right here. So here's the summary of the model. This is the formula, and it's important we can write out the regression equation. So let's do practice right here of writing out the regression equation. So let's do a practice. Let's say practicing writing out regression equation. So there's a trick. I think, you know, I'm gonna try something here. Let's try something. I want to see something. Okay, let's try this. So the formula is y hat equals b0 plus b1x. I wonder if it is... No, it doesn't work with that. Let me see here. Let me see something. Subscript in LaTeX. I want to make this look all pretty. So subscript in LaTeX. How do you do a subscript? Well, is it EXP? No, that can't be it. They're saying type. Oh, that's it right there. Okay. So they're saying you just do an underscore and then you do the open bracket. There we go. That's it. Nice and easy. It's an underscore. I wonder how you, well, the caret's the raise to, so that's going to work. If we want to raise to something, I bet it's the caret. And then hat over, put a hat over a letter in LaTeX. How to type this? There goes. Someone's asking. Was it just that also? And LaTeX makes it easy. Or backslash in the text mode, in the math mode. So people are saying, because I want to do y hat. So let's try this right here. Caret. Nope, that raises it. Someone else is saying, oh, someone's saying backslash on it. Nope, I didn't do it. Backslash verb? No. In text mode or similar in math mode. Why is there so many different ways of doing this? Why is there wide hat? Okay, wait. So they're saying, yeah, it didn't work. I've got the red bracket on it too. Someone's saying hat. Nope. Because that should, okay, that does that. Verb? No. A few more times. Okay. None of these work. None of these work. I'm looking at, this is very important to me as no one's here. Yeah, they're showing this right here. It says backslash caret. And then, so doing backslash caret, and that doesn't work. Well, that person didn't help on Stack Exchange. Here's another person. They're saying backslash wide hat. Oh, look what that did. That did it. But then how do we... What? There it is. There we go. We did it. We figured it out. We figured out how to write in LaTeX. Very important. Not very important. But this is the regression equation right here. And the regression equation, when we look at it right here, is y hat, which is the predicted value of y. And then we have b0, which is the intercept, and b1, x. And sometimes people put x1 on this. So we can even do, and I'll explain why it's x1 here in a second. The reason it's x1 is because it's the coefficient of the first x. The b1 is the coefficient of the first x, and the first x is x1. This will come into play more when we do multiple regression, but this is the model. And let's go here and take a look. And in our model, we are predicting next year's wins. So we could go ahead and substitute this in here. So if you see now, that's a bummer. If we go and put this around this, will it do it? That's close. Oh, it does it around it, but it's just not. It's basically over. It's a hat. I'll take it. That works. Next year's wins, and will it not do it? It does. Okay, I thought I typed wide hat before. You have to do the backslash, apparently. So there it is, the next year's wins predicted. Now we need the coefficient of the intercept, which is going to be this value right here. We need the coefficient of the slope, which is going to be this value right here. We're just replacing values, if you notice, as you watch this. And then x1 is going to be wins. Very important as you just watch this process right here, where we're plugging in the values. We could put a star between these if we want, just to show that they're being multiplied together. But this is going to be the equation. And I think if I knit, let's see right here. Will it work? It doesn't display them. So let me try this again, but let me try with the double. Now it displays it in line. Okay, so let's see right here. As no one's here, we'll just keep practicing. And yeah, now it does. There you go. We've got our regression equation. Good practice right here. Make sure you can see and understand the differences between these. Can I not zoom in? Can't zoom in. The differences between these are the top one is the kind of general format of the regression equation, that the predicted value of y is equal to b0 plus b1 x1. The x1 is not needed at this point when we get to multiple regression. Pretty important to make sure we know that the coefficient of the first x is b1 and the first x is x1. And then when we go down here, we have predicted next year's wins, which is the y hat variable, is equal to the intercept right here. And this whole thing is the value of the intercept. And then we have the slope coefficient, which is b1. And then we have the wins, which is the x variable. Now you have to know where this is in the output. Just take a look at what the output says. This is the estimate of the intercept. It's the estimate of the intercept. So that's b0. This is the estimate of the coefficient for wins. So it doesn't call it slope, but remember the x variable has the slope with it. So this is the estimate of the wins coefficient. So very important we know that. The standard errors we'll be using next week. The standard errors will be used for confidence intervals. It's your uncertainty in your estimates. So that tells us about how much uncertainty we have. The t ratios right here, if you take your estimate and divide by your standard error, the t ratio is a ratio of the two. I call it a t ratio sometimes because it's the ratio of it, but it is a t statistic. But you can get any of these t statistics by taking your estimate, dividing by the uncertainty, and finding the ratio of your estimate to your uncertainty. Now, the bigger the t statistic, if you notice this one's more larger than this one, the bigger the t statistic, the smaller the p-value. 2 seconds right here. I need to make like a Mario screen or like something here. You need to make a Mario jumping back and forth screen. And the way this works is if your t is in the middle, or let's say your t is right here. When this test is run, it does the absolute value of it, and then it shades the outside. So the closer the t is to 0, the bigger the p-value. So the t would be closer to the center, and the p-value would be bigger. And look at how this works. If the t is equal to 0, this would be equal to 0. The estimate would be equal to 0, which means your slope would be equal to 0, and that's the least significant line. And the least possible significant line would have a p-value of what? The least possible significant line would have a p-value of what? You would land right here on 0 for your t statistic, and then the absolute value would go to 0. And then we'd shade this, and we'd shade this. And the p-value would equal 1. So the p-value here is 1 because it's the least significant line possible. And yeah, so if we saw that, keep going back to my mixer right there. If we saw that this was equal to 0, then it doesn't matter how much uncertainty we have a slope that's 0. and then the t-statistic would be 0, and the p-value would be 1 because it's the least significant possible slope. So understanding the relationship between these variables is pretty important, that the bigger the t-statistic in terms of absolute value, the smaller the p-value, because that's going to put less area outside the curve because you're saying you're further away from 0, which is the value we are looking at here to see if 0 is the true value. And one other note to have is that the significance of the slope is the significance of the model. So you can see right here, this p-value is this p-value because the slope is the model. The x variable is making the model. We've got r squared and all this good stuff. So let's go through the rest of the output. We have here the residual standard error. So I think this one's on the assignment, but the residual standard error stands for when this model predicts next year's wins, it typically misses by about 3 wins. The residual standard error is the typical miss the model makes when it's predicting the y variable. So when this model predicts next year's wins, it typically misses by about 3 wins. Now, what's interesting is we can visualize this and see this. We're going to make the plot really big right here. But let's go to visualize our model, and let's see what a typical miss of about 3 wins means. A typical miss of about 3 means, on average, these residuals are about 3 away. If you look where the line is at and you go 1, 2, 3 down, that's about towards the center of where this interval is at. So a typical miss of 3, if you go up here, 1, 2, 3, because this is about at 5 right here, and that's about 8. So if we trace upwards, we can see this is about an average of these points, distances above and below. It's not exactly doing it that way, but you can kind of think of it as, like you've got some up here and some down here. Well, it's about averaging to here. And so one of my favorite things to do is to say, okay, if that's how we do it, or that's how we can get a good estimate of it, let's try doing it ourselves. So let's try to predict, predict offensive total yards. So we're going to go here. Let's do a whole new model on it. We're talking about residual standard error right now. So here's our model. And let's predict offensive total yards. And x1 dot, what I'm going to do? I'm going to cheat. I'm going to do it the easy way. Attach ex3. This attaches the vectors to the global environment. So now I type x1 dot, offensive total yards, x5 dot. Sure, now we have another model. I'm going to visualize the model. I'm going to take a look at it. Oh, cool. Awesome. Okay, this is a really good model. I don't even know if I'd call this heteroscedasticity because there's fewer points. Those aren't really extreme outliers. This is a very good model. This is, if you're making regression and you get this model, this is kind of the jackpot model because you're like, okay, it might be a novel relationship, something we don't really care about. Like, yes, first down passes explains total offensive first yards. It kind of makes sense because the more first down passes you get, the more opportunity you have to get first offensive yards. So there is a kind of cause and effect, I'd say here. And you're like, wait a minute, Brian, you say don't say cause and effect. Well, getting first downs leads to more offensive plays. Like the way you get more offensive plays is you get more first downs. So there is it causes more first downs and it causes more plays, and more plays cause more yards. So I think we can probably see the causal connection right here. But it doesn't mean, it's definitely associated, and you won't say you will. We could talk about the interpretations of these in a moment. But when you look at this, you see that the spread of this, about a half width of this, is maybe about 6. I'm trying to think. If you were to look at this, you'd say, okay, you go to it there. I'm going to go with 5. I'm going to go with 5.5. I'm going halfway between it. Okay. So I'm taking a guess at the residual standard error just by looking at it, by saying about how far is that apart. I'm saying 5.5. Oh, I should have went with 5. I'd have been closer. I'd have been closer with 5. And then I should have gone with 4. And that'd have been really correct. I thought I was too high. I went lower. So it's saying that the typical miss the model makes is about 4, which is really good. We typically miss when we predict offensive total yards, we typically miss the offensive total yards by about 4. And that might be in units of 1,000. Or maybe hundreds. Might be in units of hundreds. So we buy about 400, and that's for a season. But when we predict the offensive total yards a team will get for a season, at least with whatever units we have right now, we are typically missing it by about 4. This model typically misses, and that's the typical size of the residual via the root mean squared error. Now, it does call it residual standard error right here, but I want to point to why I like calling it root mean square error. The reason I like calling it the root mean squared error is because a few things cancel. Root mean squared error. You've got root and you've got squared, and you've just got mean error. So why don't we just do the mean error? Well, because when you do the regression, some points will be above the line and some points will be below the line. And if you were to just take the mean error, they'd go to 0. So you'd have a 0 error if you did mean error. So we square them so they become positive, and then we take the mean of it. So the error is the residual. So this is the residual squared. And then we take the mean of the residual squared, and then we root it to bring it back to the units of the problem. You don't want to talk in squared units, so you could talk about the mean squared error, but it'd be squared units. But it makes more sense instead of saying, oh, the typical miss is 16 because that's in squared units, or the squared miss is 16. We'd say, the typical miss is about this. There's another way you can do mean absolute error. And there's ways beyond this even. Mean absolute percentage error. There's so many other ways. But this would do the absolute value. So you would just take not the negative and positive, but you would just take the absolute error right here and add up these. So and you do the mean of it. So you could just do the mean absolute error. And a lot of things have things like MAE. So you can do all these. There's a really good, I might look that up. It's a really good package that does summary statistics on regression. And I've used it before and then I always forget about it. But people who've had to do analysis outside this class have had to look at additional statistics. And they're like, hey, Brian, how do I get MAPE and MAE really easily? And I'll say, oh, there's a package that does all that for you. I mean, we can compute it because watch this. If we want MAE, all we have to say is, here's our model, and we need to solve for the residuals. Well, here we go. The residuals of the model is this. There's the residuals. So we want to do mean absolute error. Well, the error is the residual. So we want to take the absolute value of it. And then we just want to take the mean of it. So now we have the MAE. That is the mean absolute error right there. And we just did the error, which is the residual. We did the absolute value, and we did the mean of it. So we could also do by hand the root mean square error, root mean squared error, and just do it in the order it's in. Well, here's our error here once again. This is the error. Let's square it. Let's take the mean of it. And then let's take the square root of it. And if you notice, we're just going in the order it exists. And there's the root mean square error. And let's check it with ours. We're going to run summary of the model. And then let's check it. And there it is. Looks like we don't have all the decimals, or they're carrying their decimals differently. But it says residual standard error here. I don't like that that's different. Everything looks accurate. I think it's just either one of the two is carrying more decimals, which I wonder how they're getting different numbers. It does concern me that we're off by 100th. I don't like being off by 100th. Usually if the last number's off, I don't mind. We have all the residuals. We're running the same model. So we're squaring it. Root mean squared error. Yeah, let me look at something. Let me look here. Summary statistics for regression package in R. I don't know if Stargazer. Which one is? Someone's got a package here called Stargazer. I do not know this package. See if anyone's in the chat. No one's in the chat. Descriptive statistics. Another person mentions Stargazer. We're using the MT-Cars data frame. It's a pretty... Well, two people have suggested it, and this one is Princeton. So let's see about this Stargazer package. We're going to find out if Stargazer package is worth it. And so, looks interesting. You can make tables of stuff. Regression models in text format. So they're doing 4 models? Why would they do 4 different models? That's a lot. It's a lot of output. So it's called Stargazer. The function is called Stargazer. Let's find out what Stargazer does. Please cite as... Okay, this guy made it. Thank you, gentlemen. Stargazer, and... Whoa, holy moly. That's not a table. So let me take what they put. Dependent variable label, covariate labels. Well, they definitely made it not user-friendly as far as I can tell so far. Regression models in HTML format. I have no idea what this is printed out. I do not know how to use this package right now. So for the output, you have to output type HTML. They're doing 4 different models right here. They have 4 different models. Yeah, I don't like this package so far, or at least until I know how to use it. Let me look at the, here's their original thing. Let me run a data set they say to use. I think we have the, oh, I don't like the way that reports. Are they doing it when they knit it? Is that what it's going to look like when you knit? Oh, I have errors in here. I have these. It's not liking those. Error on line 22. Oh, installed up packages. I'm trying to install something into an HTML file. Okay, that looks craziness. To output the contents of the first row. I do not understand how they're... Okay, I don't like this package. Sorry, package everyone loves. Until I know how to work the package properly, I'm not going to use it. So descriptive statistics, where is it? Extra regression tables with Stargazer. Everyone likes Stargazer. I need to look into the Stargazer thing. If you're here, feel free to ask questions. It's like dead air on, or is it MAE? Let me see here. Metrics. That's the one I've used before. Metrics. So I think I should have that on here. Nope. Model metrics. Oh, that's okay. I have this on here. And let's go to the model metrics. There was one I found last time. So there is all these functions. There's MAE. So hey, we got an MAE function now. So we should, is there, yep, do we have, there we go, MAE, did not run anything. Error in MAE, argument predicting is missing with no function. Oh, we have to use, let me look at the MAE function. Page 10. So the MAE function, you have to do all that work. I already did all the work. MAE, mean absolute error, here we go. And examples. You do the actual and the predicted. Oh my gosh. So the actual is going to be, we're predicting this. So there's the actual and predict using model M. There we go, 3.0947. And this is this one. There we go, exactly what we have. And then RMSE, well, RMSE is probably gonna be the exact same thing. My are using what I wrote. So, regression, here we go. It's not probably the latest one. What package was I using? This doesn't look to be it. I'll put bookmarks throughout this video. Well, this is not so bad. Regression diagnostics. I have too many packages here. I have so many packages in R that I can't remember the package I need to use. So, what did I do? Influence, plot, plotly in R regression. Okay. If you're here, feel free to say hi. I'm just doing some work and looking through some regression right now and seeing if I can find the package I used. So what was it? Myers plot regression plotly R. How did I find it so much last time? I found it so easily. Such a bummer. What is the name? See all packages. Let's see all libraries in R. Find installed packages. Here we go. Installed packages. No. I think if I do this. There we go. And we run out of stuff. Let's go here and store this as a list. Let's go to df. Oops, wrong thing. I think this will store as a list. Okay, good. Now we can go ahead and look through our installed packages. So here it is. A bind, a rules. I have too many packages. Was it Berry functions? I did that one recently. So many packages. R is going to be important for regression. Let's see if we see. Oh, I hate how it keeps changing perspectives. I'll be. Wish I had a little summary of what every one of them did. Trying to remember. Can't remember. What was? You know what? I wish I have it in a video. So I'm gonna have to like go back and look to the video. If you're here, feel free to say hi. I've just been kind of looking through regression stuff right now, talking through a little bit about regression and trying to remember where certain packages that'll do a certain plot. I'm looking for hats matrix, hats plotly in R. I don't see it. That's a bummer. So we were talking through the regression output here. We'll go back to the regression output because I cannot find it. And so our regression output, we have a different equation now. And whenever we do the equation, we just need to make sure, I keep reviewing this. I've seen a bunch of people get stuck on this. You need to know what the output is. The output right here is showing you B0 and B1. And as we talked about previously, so I am repeating myself right now. We talked about this is our uncertainty in B0. This is our uncertainty in B1. This is the standardized coefficient of B0. This is the standardized coefficient of B1. We get these values right here by dividing the estimate by the standard error. And then, it's just the graphics warning. So let's do this. And we have right here the p-value. And the p-value tells us if it's statistically significant or not statistically significant. So right now we are predicting the offensive total yards by the offensive pass first downs. And what we see right here is a very strong regression with 64% of the variation in the offensive total yards explained by the variation in offensive pass first down. So tons and tons of the variation explained in the y variable due to the x variable. So really good stuff right there. And we have here the adjusted r squared. We haven't talked about this yet in 320, but the adjusted r squared is r squared adjusted for how many variables are in the model. It's basically r squared with the penalty term. So you know what? Let's do that right here. Let's put that in the video. Adjusted r squared equation. So I'm going to bring up the adjusted r squared equation and let's take a look at it. And I don't like that version of it. Oh, here we go. Here's a good version, which looks like our notes. Cool. Let's go grab this. Let's bring it over here. And let's go to a Word document with it. So this version right here is the adjusted r squared. It's got the notation like we have. And let's talk about what this adjusted r squared is. So when you look at this r squared, I'm trying to think. Let's just actually go grab our notes version of it. Yeah, let's do that. It's so early in the morning. Let me go grab the notes version. So linear. Don't know if anyone's here. It's a Friday. Is everyone else waking up? I am waking up still. Brain's got to go. Brain's got to turn on. Got to go to 100%. Let's go grab the adjusted R squared. You can write it ways it makes a lot more sense. Here we go. We'll be talking about this next week. Class is over. Why is it not finding it? Oh, I think I know why. Wrong notes. Nobody's here. Okay. Where do we put the adjust R squared? Not there. Oh, I think I know why I can't find it. I think because we don't talk about it till multiple regression. Brain is just not on this morning. Because, oh, it's good to mention it now. It's more of a multiple regression metric because adjust R squared is for the amount of variables you have in the model. So if we have more variables in a model, there we go. There we go. There we go. Here we are, adjusted R squared. So let's take a look and let's see the much easier version to look at. I just want to compare them. Yep. So yeah, that's right here. You can see, I like the way it's just displayed in our notes way better because R squared adjusted is really just this right here. And that's what I wanted to display visually so everyone could see. But R squared is just R squared minus a penalty term. So R squared adjusted, and I misspoke, R squared adjusted is R squared minus a penalty term. R squared adjusted is just going to be basically a R squared that is lower than the original R squared. And when you look at the equation, you can kind of make sense of what's going on right here. Because what we're going to do is we're going to look at the remaining unexplained variation. So here's what we explained originally. And then we're going to subtract off the remaining unexplained variation, but we're going to weight this. We're going to weight it by how many variables are in the model and the sample size. So if you put a ton of variables in the model, this will make this equation kind of weight more towards this, towards what we've unexplained. So the mathematics here hopefully make a little bit of sense that the more variables you have in the model are kind of a penalty. If you put a ton of variables in the model, variables with a lot of variables will do better. So as this k gets bigger right here, what you'll notice is the penalty term gets bigger. You could just think of this as a number. How does it work? If this is 80%, this is 20%. This is the unexplained variation. This is what we have not explained. And then we're going to take and multiply it by a term right here based on how many variables are in the model. And then we're also going to weight it towards the sample size. So if you have a large sample size, the variables won't be that big of a problem. If you have like 1,000 sample size and you have 5 variables, it's not going to really damage it. But if you have 5 variables and you have 10 observations, then you're going to see a much larger penalty here, and you can actually get a negative R squared. So R squared adjusted. R squared adjusted doesn't have an interpretation. R squared adjusted is, hey, what's up, AW? You're finished? Or am I finished? It is Friday morning. I think we're all waking up. Good to see you here, AW. But we have here the R squared adjusted. If you have any questions, let me know. Let me know any questions. I might go for 1 hour today because it's a Friday morning. 201 had their test, and 474 is getting ready for their take-home test. So lots and lots of work, and might see everyone's doing that. I'm going to send out a practice test for 474, and I was working on that. But we're talking here about R squared adjusted. And the biggest thing is understanding what this is. So r squared adjusted is what r squared adjusted is. R squared adjusted is just r squared adjusted for how many terms are in the model. So when you think about it, you're just looking at a version, and I just don't like the way this is written right here. I'm sure it mathematically solves out to the same, but I don't like that. Don't like the way it's written. So because things should make sense. When you look at it, it should be like, okay, this is what this is doing here. And that's why I really like our notes version. I was trying to find one similar enough to our notes. I have so many different things open because I was like, oh yeah, it's in multiple regression because we have more variables in the model. You can calculate it for a simple regression, but it's not as important because you're not really adjusting for how many variables are in the model. I mean, you are, but there's one variable, so it's not as important to adjust for that. But this is a much fairer look at your r squared because think about this, and we showed here previously, if you put a whole bunch of variables in the model, you can get an r squared of 1. So achieving an r squared of 1 is not that hard. You just put a bunch of variables in the model. And I could probably do this with our NFL model. I'll go right here to the NFL data. Let me go to our model, and I'll put all the variables in. So we're going to predict the total yards a team gets. We're going to go right here. We're going to put all the variables in. And let's do a summary of this model here. And the summary of the model has an r squared of 1. It has an adjusted r squared of 1. And then it says, essentially perfect. Summary may be unreliable. Thank you. R is telling me, what did you do? And you might even say, well, why is the r squared adjusted 1 also? Well, that's because of the way it's being computed right here. When you get an r squared of 1, just think about what happens to the mathematics here. So with an r squared of 1, this would be 1. And then the penalty term right here, 1 minus r squared, is going to be 0. And that's what we're multiplying by this. So if this becomes 0, you still get an r squared of 1. But we have a ridiculous model right now. This model is completely unreliable, and we'd probably see it in the, I'm hoping the RMSE has a really bad metric, because the RMSE also tries to account for this. Oh no, the residual standard error is also very tiny. I feel like, wow, this model does perfectly. This model explains everything. But if you use this model, I'm thinking in practice, but this model is a saturated model, we would call it. It has too many variables inside of it, and it would not be reliable. And this is one of the things people can do with statistics and say, oh, I got an r squared of 1, and my typical miss is 0. Well, how many variables did you put in the model? You know what we need to do? We need to look at the AIC of this model. Oh, AIC is probably going to be really good too. Yeah, AIC is really good. Can we do AICC? AICC is for small models. AICC is not in its vocab. Oh, wait, AICC. Can't do it for this model? Well, I'll be. You can do AIC, though. AUK is information criteria, but you would never obtain this model without completely overfitting the model. And you could also look at this. Well, there's one way with predictive analytics to know that this is overfit, and that's actually to try it out on new data. Maybe it's not overfit. Maybe it actually works. But this data right here, this model is, if we use it on new data, something tells me it's not going to work. It's a ridiculous model. And we have aliased coefficients right here because it can't make an estimate because there's no more variation to explain, or these are completely overlapping. Well, yeah, that's what they'd be. They're completely overlapping in what they explain with the other variables. Thus, there's no more variation because the other variables have already accounted for everything that the variation is included in this variable here. So lots of stuff going on right there. Let's see what else to talk about. I'm just having some fun this morning, working on some stuff. Look at all the teams. We have indicator variables. So this is kind of understanding what's going on right here. You might say, wait a minute, Brian, tool 1, we learned QQ straight enough, no outliers, plot doesn't thicken. Well, what we have right here is indicator variables. It's treating this like a 1 or a 0. The team is either Atlanta or not Atlanta. So it actually turns these into quantitative variables. And so we can actually use a categorical variable by turning it into a quantitative variable. And I think we should be able to visualize that. Let's go here and do a little visualization on that. So this has kind of just been a fun talk about regression this morning, kind of rambling about regression. This whole video is that. If we go over here to survey 10 and we want to predict, let's go here to M, save into LM. And you know what? I bet you we could show it this way. If we want to predict somebody's height and we use gender, we could recode male and female. So this is a little 474 help right here. We could predict somebody's height using their gender, and data equals survey 10. So we have a model right here, and you'll notice we get a coefficient, and we have a coefficient male. So if somebody is a male, that'll be 1, and if they're not a male, 0. let's do this. Let's go if else. And let's go here to survey 10 gender. What? I did do $. Gender equals male. Let's do a 1, if not 0. There you go. And then let's go here. Survey $, survey 10 $. And let's go gender quantitative. And let's store this as a quantitative variable. Now it literally is a quantitative variable. And let's make a second model right here. So we're going to make model 2. This will be model 1. And in model 2, we're going to have model 2 use gender quant, which has been added on here. And now, if we compare these models, here's the coefficient of gender male, and it should be, if I've done everything correctly. There's the coefficient of gender male quant. Hey, what's up, Ahood? I'm showing a trick right here about how a categorical variable can be used as a quantitative. So happy Friday, Ahood. Good to see you here. We had AW. I don't know who AW is, but they stopped by to say hi. And so if you notice, I took a categorical variable, which was gender, and I made it quantitative. Because if somebody was male, it's a 1, and if somebody's not a male, it's a 0. And so this is what this is originally doing right here, where it says gender male. This is a categorical variable as an indicator variable, which we'll talk about. Do we talk about that with simple linear? That'll be coming up. Indicator variables. No, I think is that after multiple? My brain is just, there's been so many things. Do you have any questions, Ahood, about the assignments? Feel free to ask. Just kind of showing how we can do more advanced things right now with, and we won't actually recode the variable. I recoded it to be a quantitative variable just to show this coefficient right here is the same as this coefficient right here. And all you're doing is just assigning all the males to be 1 and all the not males to be 0. And if you visualize this model, you get the following. So you can see here's the males and here's the not males. And that's what's going on right there. It's just doing an assignment of 0 or 1 if somebody is or is not the indicator variable. And yeah, it's pretty interesting. Could do a lot of other things right now. Just thinking about all the things we could do. One big thing we should know, which will be coming up right here. Let's talk a tiny bit about this output. It's a good way. I don't know if anyone has questions, but feel free to ask. This output's going to be super important, and it's going to be this. So this output we will see next week. And here it is. It's the check regression output. So here's the steps for doing check regression. So it can be in this video. All this video has been pretty much me just rambling the whole time. With the check regression, what you're doing is you're checking 3 conditions. We are checking the first condition, which is right here. Are the residuals normal? Condition 2, is the line a good fit? Linearities first. And that's last. So is the model linear? And then equal spread. There we go. Equal spread of residuals. Cool. So you can see all 3 conditions right here. I give this in the output during the test, but we have the linearity of the model, the equal spread of the residuals, and are the residuals normally distributed? Now the steps for this, let's talk about the steps for the checking. Steps for checking. So first thing you do, p-values should be above 0.05. That's what confuses people. People automatically think low p-value is good. They say, oh, the p-value is low, reject the null, that's good. No, that just means you reject the null. And the null for this is linearity is good, equal spread is good, and normality is good. So the null is that these are good. So if you reject the null, you're saying there's a problem. So I'm saying there's a problem. I reject the null that the linearity of the model is good. There's a problem with linearity. I reject the null that the equal spread of the model is good. There's a problem with equal spread. I reject the null that the normality of the model is good. There's a problem with the normality of the residuals. So if you look at this, you can see some of them right here. And so once we reject the null, so we'll go here. If any nulls are rejected, look at sample size. If sample size is 25 or less. Stop. More than 25. Continue. Okay. So we have to look at our sample size. And our sample size right here is, there we go, 699. Since our sample size is 699, we can continue. If you have too small of a sample size, then violating the conditions, you just want to stop. You want to say, okay, this is a small sample size. We violated the conditions. We're just going to pull the plug on this regression. Now, you might say, well, why would we continue if the sample size is larger? It actually goes to the concept of statistical power. If you have more observations, you're more likely to reject the null because you have a more powerful test. It's like collecting more data. You're more likely to find results. And because all models are wrong, we're probably going to see that this model is incorrect, that the residuals are not normal, that the linearity is bad, that there's unequal spread. We're going to see that there's an issue because all models have issues. So it's highly unlikely you'll find a good model if you have a lot of data. And then it becomes, how bad is our model? Because the tests do generally reject. With that in mind, if you have a small sample, the problems are super big probably. If there's a small sample, you'd probably look at the plots anyway and be like, whoa, these are super big problems. But we've kind of said, no, don't even look at the plots. If the sample size is small, just stop. The problems are probably too big. You need to just not use the model because we want to be cautious here. We're going to use a model to kind of explain reality, and that's kind of crazy enough in its own right. So if we have a sample size of 25 or more, then we would go on and look at further things. So 25 or more, it says here, 25 or more. Oh no, so I wrote the wrong thing. If sample size is 25, is less than 25. Less than 25 is more, is 25 or more. If 25 or more. Continue. So, and it's like 25 or more. If you were to stop at 25, it wouldn't be that big of a deal. These are arbitrary breakpoints anyways. Someone else might have a guideline of 30. So it's just what we've kind of decided, like, hey, if it's 25, less than 25, stop. So if it's less than 25, stop. If it's greater than or equal to 25, continue on and look at the plots. So that's step 3. Look at the plots to see if they are okay. So we fail the linearity. We fail the equal spread. We fail the normality. So now we're going to go and look at the plots. So plot number 1 only looks at linearity. Plot number 1 only looks at linearity. The linearity of the model is how well this line cuts through the data. You can see an issue of linearity where the line is not cutting through the center right here. So there's a bit of non-linearity at the end of this model, and this is also apparent when we look at the visualization. So let's look at the visualization, and at the top end of the model, we should see an issue with linearity. And do I have this as model 1? I do. So you should see at the top end of the model here, and I need to make it bigger so we don't block it with the sign. And, oh, you know what I can do? I can do this. Loc equals that. There we go. And you can see the linearity issue at the top end of the model, that the model is not going through the center of the points. There's a bend in the model right here. We can even go further and do a thing like choose order. And with choose order, does it have Loc? Yeah. Choose order, you can see the non-linearity of the model at the top. So you can see it bends, and these are higher order polynomials. I don't think that bend's appropriate. That's kind of overfitting to that one outlier. But we do see kind of a polynomial bend. And we could make this even easier to see by going here and going to max order and do a max order 2. And there's the polynomial or the quadratic fit versus the linear fit. So examining just the quadratic fit versus the linear fit, I do see that the quadratic fit has the bend, which we're seeing at the top end of the model right here. And this all goes back to this right here. The whole point of this was to talk about this little section where we see a bend in the original model. So that's the residuals right there have a bend, and the linear model looks to have a big problem. That's a big issue. That might be enough for me to toss this model. I mean, if I would just go to the polynomial model probably, but that looks pretty bad right there. We also see an issue right here with the normality of the residuals. So plot 2 and 3 are going to be the normality of the residuals. And so we see normality of residuals right here have a problem, and they're all right up here. That's fine. It's within the bounds. That's way better than down here. So this looks to be the issue, and that's coming from the low residuals right here, because you look, this point goes into this, and these 2 points go into these 2 points. So we're seeing issues with the low side of the normality of the residuals. There's kind of too many on this low side, or they're too far away. And the last condition, equal spread, can be seen here. And I don't see that much with equal spread, even though we failed it. I mean, it might be getting thinner, but it's of the the least of my concerns. I can't really see a point where I'm like, okay, it's getting thinner. But I'd be more concerned about, first off, the linearity of the model, second off, the normality of the residuals, and third, like a not as big of a problem is going to be the equal spread. And did equal spread give us the highest p-value? Higher p-value is better for these. Equal spread did give the highest. Everything else was estimated to be 0. So equal spread was a really small p-value. It was 0.0. It was 0.0009. So it's a very small p-value, but it was better than 0. And so what you want to see is you want to see p-values. Let's show what the p-values should look like. If we get good p-values, and I should be able to make this if I go to y will be random normal numbers. And let's go 1 to 100. I can make an equation right here. Let's do x goes from 1 to 100. And then y will be equal to, let's go to 10 plus, and then, I can't think, 2.3 times x times random normal, and then random normal plus random normal. There we go. So now I made an equation right here with an actual slope to the line. So this is the equation. It's got some randomness on it. So let's go here to m, save into lm y tilde x, which we talked about earlier. Let's go to visualize our model. And we should get a ridiculously good looking model. That is too good of a model. So let's go here to a mean of 20 for these and a standard deviation of 15. Still too good. Don't like it that. There we go. So this is a ridiculously good model. Cool. Still like it. Okay, this, you might say, oh, we got this one outlier. No, this, if you get these models, this is amazing. This is top tier model. The equal spread is amazing. This and this, that's just your 99.7. You just get one thing that's a little bit further out than most. We have 2, and that's not the end of the world with 100 points. So when we do the check regression, we should see high p-values. And do we? Not enough duplicates. So, because it needs multiple values of the same x value. You know what we could do? Rep this 3 times. Oh, we fail it. Really? Linearity failed? That's interesting. And normality failed? Whoa. Yeah, these tests are sensitive. Yeah, wow, this is a perfect example. Can you please go over interpretation and coefficients, compare the average? Yeah, let's do that right here. We'll do that. You bet. We'll do that next year, and I'll finish this up, and then we'll do interpretation and coefficients. Check this out, Ahood. How good does this QQ plot look right here? How good does this QQ plot look? I'm glad I did this example. I've never done this. I was just thinking of new examples I've never done. How good does this QQ plot look for normality of residuals? Do the points mainly follow the line? Do the points mainly follow the line? They pretty much do. The points mainly follow the line. So this actually looks really good right here. And then how good does the equal spread look here? I mean, except for this gap right here, I'd say the equal spread looks pretty good. And then the linearity looks pretty good. But here's the issue. We actually fail, we fail the normality of the residuals. So it's saying the normality of this plot right here is pretty bad. And then it's saying the linearity of the model is also pretty bad. So because of the large sample size, which is, I just went over the steps on how to do this. Because of the large sample size, it's saying this line is not a good fit through the model. And remember these steps, you might want to rerun, this is for next week, but we're asking, check the p-values first. So we fail the linearity condition, we fail linearity, and we also fail normality. And then we have to see if the sample size is larger than 25, which it is, and then we have to see how the plots look. So when we look at the plots, we want to ask, okay, how bad is the linearity? Linearity looks to be fine. How bad is the equal spread? Or normality, wasn't it? Normality looks to be fine. Which one did we pass? We passed equal spread, yeah. So you have to look at the plots because with larger sample sizes, these tests just almost always go to fail the test. You just almost always fail the test. Yeah, look, we're failing linearity every time. That's insane. And the linearity never looks bad to me. I'm shocked linearity fails. Let me try this. And then we'll go to the interpretations. Whoa, and then you fail every time? We are seeing issues with outliers. That's so crazy. You know what it might be? It might be the amount of variation I put on this. No? Wow, these tests are so sensitive. Man, even using a real equation. That's so crazy with the randomness on it. One last thing I'm going to do. So crazy. So interesting. So interesting. Let's talk about some interpretations right here. So I like doing theoretical stuff. It's pretty cool. See what happens. So can you please go over the interpretation of coefficients, compare the average or expected value of y between individuals? Yeah. So let's look at here two teams. We were doing NFL data just a moment ago. So with the NFL data we were doing, we have here, we could do this one right here. Let's predict somebody's height by their number of tattoos. Let's do weekly hour video games. We'll do weekly hour video games. So weekly hour video games not found. I can't spell apparently. Weekly H or video game. Oh, I did games. Typos, not the fun way to do it. Okay. So when we interpret this coefficient, we can interpret the intercept as for individuals who play 0 hours of video games, we'd expect on average for their height to be 67.089 inches. So for individuals who play 0 hours of video games, we'd expect on average for their height to be 67.089 inches. But then when we do this one right here, the interpretation of this coefficient, we'd need to say two individuals who differ in their x by 1. So let's write this down. So two individuals, or whatever the y units is. Not units, but y. Where the y variable is. Maybe it's a team. I'll do an NFL team one next. Two individuals who differ in their x by 1 unit are expected to differ in their y by b1 units, where the individual with the larger x is expected to have the larger/smaller y. You have to pick larger or smaller. So watch as I try to do this right here. Two individuals who differ in their weekly hours of video game by 1 hour are expected to differ in their height by 0.26 inches, where the individual who plays more video games is expected to be taller. So does that make sense right there, Ahood, if I'm going through this interpretation where I say, yeah, two individuals who, have a difference of their video game hours of play by 1 hour, I'd expect them to differ in their height by 0.26 inches, where the person who's playing more video games I would expect to be taller. Because the units of x right here would be its weekly hours of video games. So you always go by the units of x. So right here, I don't say by 1 unit. I would say by a difference of 1 hour, because we're always going to put it in context. We'll always say like the units of x. So two individuals who differ in their weekly hours of video games by 1 hour, or two individuals who have a difference of their hours of video games by 1 hour a week are expected to differ in their height by 0.26 inches, where the individual who plays more video games is expected to be taller. Does this make sense? I'll do an NFL one here in a second, and then it won't be video games anymore. It'll be a team. So I'll get that question kind of loaded up right here. We just need to change. I think we'll do, there's wins. There we go. So now, sure, that's fine. So now we're predicting next year's wins. So when you interpret this, you need to make sure we're talking about two teams in the NFL that differ in how many wins they got this year by 1 are expected to differ in their wins next year by 0.3, where the team that had more wins this year is expected to get more wins next year. And does that make sense? Two teams in the NFL that differ in how many wins they got this year. This year are expected to differ in their wins next year by zero point 0.3, where the team that had more wins this year is expected to get more wins next year. Can you go through another rundown display of trees, decision trees, or tree charts after the screen stuff? Not sure what they were called. Yeah, decision trees. Yeah, Charlie, of course. I'm gonna try and make a video before the Kahoot. I've got some, but we'll see. And Charlie, thanks you for asking, Charlie. I've been trying to make more mods. I think maybe with the max amount of mods, such a bummer. I'd have to I don't know. I'd have to go and clear out mods. Maybe you only have 500 mods, and I might have hit the max mods. YouTube's like, why do you want 700 mods on your channel? But does this make sense, Ahood? Two teams in the NFL that differ by how many wins they have this year by one are expected to differ in their wins next year by 0.3, where the team that has more wins this year is expected to have more wins next year. Yep. And just this right here, I think, is a really good practice interpretation. And just make sure you do the units. Make sure when you say it, it makes sense. Because if I just say to you, two teams that differ in their wins this year by one are expected to next year differ in their wins by 0.3, where the team that had more wins this year is expected to have more wins next year, it should make sense. It should sound logical. It should hopefully you shouldn't be like, what are you saying? It should sound pretty logical. And you can always change the words, but the more people change the words, the scarier it gets, because people will be like, two people in the NFL who differ in their yards of wins. And I'll be like, what are you saying? What are you saying? So here we go. Let's go to a decision tree right here. Let's go to predictive modeling and partition. So this is a partition model, a decision tree, and we're going to take a look at the data right here. So we're going to predict, let's predict, I'm trying to think of something we can predict that wouldn't be too hard. I think that's the one we're doing for I don't know if this is the data set. It might be the data set. I don't want to do that one. Let's predict. I've done all the ones I know that work. That's such a bummer. Let's predict if someone's broken a bone. But didn't I try to do this one and it didn't work? I've done that one multiple times. I swear it worked. It must be with a different data set. So let's predict if somebody has broken a bone before. And the number one explanatory variable if someone's broken a bone is how much people exercise. So this is, do you exercise 30 minutes 5 days a week? Fraternity, sorority. Oh, well, and then remember, the Y variable will be one variable. So good questions here, Charlie. The Y variable will be one variable, and then the X variable will be all the X's except for indicators and things that act like indicators. And this doesn't have any indicators. Is it? Let me see. I think I have a different data set, and I think that's why this one doesn't work, because, oh, there we go. Where's that pivot data? I think it works with the pivot data. 2 seconds here. Class is not over right now. I'm going to go grab the pivot data from the 201 site. I think the broken a bone is in the pivot data, and I think it'll work with that variable. And so when we do a decision tree, we take one Y variable, and we want to be quantitative or categorical, and then we take all the X variables, every single one of the X variables, except for things that are identifiers or things that act like identifiers. And I can't say that enough. Don't take things that are identifiers or things that act like identifiers. Those should not go into your model. So I'm about to have the data in here. Data is in. Data is good to go. Let's do this. So we only take pie flavors could be similar to an, yeah, exactly. Yeah, it's something like that where there's so many levels of it. And so let's go right here and let's see, do we see any indicators? And Jump's got a really cool thing right now where you can look at the variables. And so we can kind of look at this right here. Whoa, wait a minute. I think I see an indicator. Do you see an indicator on here, Charlie? Do you see anything right now that looks like an indicator? Do you see anything that looks like an indicator automatically right now? Do you see any indicators on the screen now? Is there an indicator on here? Do we have any indicators? Well, weight is quantitative. So weight would be quantitative, even though there's a whole bunch of weight values, it's going to be quantitative. And you might say, because it sounds like a trick, and here, I'll give you a hint. Wait, take a look over here. Oh, it doesn't have that on there? We've put it on there before. Original row number is an indicator, because this is basically unique for every single person. It's just their original row number. It's just indicating what row they were in originally in the data set. So we're going to remove original row number right here. That was an indicator. I'll go to another one. I'll see if I see another indicator on here, or things that was an indicator. That literally was an indicator. I swear we should have more. Did we remove them out of this data set? Sigh. We removed out the other indicators on this. That's not too many. Facebook was really big. This data set is from like 2014 or something. And we don't even have like Snapchat. We have Instagram. Instagram's not that big. Twitter's pretty big. It'd be so interesting to see what people like now. The age of people's dads, the age of people's moms, 28. 28? Someone's mom is 28? And I think we had if your parent was deceased right here. Which we might be able to highlight these people. Watch this. Let's go here and let's go to rows, hide and exclude. There we go. Look at that. Oh, I love this new feature. Rows, hide and exclude. There we go. So what is the cutoff for something to be considered similar to an indicator? That's a really good question. If you have like 20 observations and there's 10 levels to it, like if I ask people a question and there's 10 levels, like relationship status could have a lot. Yeah. And if you only ask 10 people that question, it could work as an indicator. If you have like, imagine if you had, for a relationship, you had single, dating, casually dating, long-term dating, short-term dating, went on one date, and then you have married, married for 1 year, married for more than 5 years, married for more than 20 years, married for more than 40 years. I think my parents have almost been married 50 years. Oh my gosh. And then for divorce, you'd have divorced 1 time, divorced 2 times, divorced 3 times, recently divorced. At that point, it's going to become like an indicator. If you have, a lot of times when you do stuff on relationship, and it just, since I'm engaged, I'm like, I'm engaged. And they're like, so you're single. And I'm like, no, it's not single. How is engaged single? Why do they not care about that? They ask, are you married, or are you widowed, or are you single? Like, those are like the 3 they really care about when they ask. I think it's married, widowed, single. They don't ask me widow. I don't know. I don't want to be widow. But yeah, it's so things that act like indicators would have tons and tons of levels. Quantitative things, even though quantitatives can have a lot of different things, it's quantitative. But if you have a kind of numbering system of like first person, second person, third person, that is an indicator, even though it's a number. And then someone could argue as time order relationship to it. So there's so much nuance to everything. But here's the big thing for the test. Like, let's go test specific here. Don't put indicators in decision trees or things that act like indicators. And things that act like indicators are going to have lots of levels. You will see some in your data. You know what? I could go grab that data. Let me go grab your data right here. Let's go grab the data. So let's go grab the data that we need to do the project. I will be making a project video later. We'll be making the project video. Project video. Project video. Should be able to make it between. Okay. So here we are. I'm not going to mention all the decision tree, all the things that. Do you see anything right now, Charlie, that acts like an identifier? Do you see anything right now that acts? Because I'm confused. Like if I ask, what's your preferred ice cream flavor, chocolate or vanilla? But if you only ask, do you prefer chocolate or vanilla, that would not be an indicator. So, but if you ask, what's your favorite ice cream flavor, that probably would act like an indicator. So something that is yes or no, or chocolate or vanilla, would not be an indicator. That's just a 2-level categorical variable. Levels is how many options there are. And then if you ask, what is your favorite ice cream flavor, that might act like an indicator. It wouldn't be an indicator. It might just act like an indicator. Do you see any indicators in this, or any identifiers? I keep saying indicator. Identifiers. Sorry if I say the other word. Do you see any identifiers in here right now that are like, that's an identifier? That is an identifier. Do you see any identifiers? You betcha. So, make that go away. Here's the trick you can use to look at them. Just kind of dropping some hints right now. This is kind of a good way to see if you see anything crazy. Remember, quantitatives are fine. Maybe. Maybe. I'm not saying yes or no. And you can look at what the variable is. So you can look at the name of the variable here. Is this helping it make more sense, Charlie? Is this helping make more sense what might be indicators, identifiers? I can't think. Identifiers. Yeah. So, and I think, that might be it. And it kind of helps to look at the distribution of it. If you look at the distribution of it, you can see in quantitatives, you don't got to worry about quantitatives. It doesn't even matter if there's a lot of there's no levels to quantitatives. It's only if the quantitative is a numbering system that you care about removing it, because if there's a numbering system, then that's an indicator indicating first person, second person, third person, just numbering off. So that's got that. Let's go ahead and do a decision tree. See, I can't use this data set because if I do that, I'll remove the indicators. So I'll probably have to make, when I do this video, I'll probably have to make, because I don't want to do all the work. I want people to figure out what I keep saying indicators, because I was doing indicator regression a second ago. I want people to figure out what the identifiers are. So I don't want to completely say them. Here's the broken bone. And so we're just going to grab a few of these. You grab all of them. Oh, did I accidentally grab the thing I shouldn't grab? Where is it at? There it is. Not going to grab that. Okay. We'll just grab these for now. So this is the broken the bone one. And this is the one that works. And there we go. We have, and darn it. It's really hard to make the selection go away. You have to click in an area that's not selected. There we go. So if you look right here, we ask people their gender, and we have male, female, prefer not to answer. And the people who are more likely to break a bone were male. The people who are less likely to break a bone were female. And then we split again, and it's on how many languages you speak. And here's family economic level. So the most likely people to break bones are males who speak less than 2 languages. The least likely people to break a bone were the females, or the people who preferred not to answer, and were middle class, lower class, middle class, lower. This is the upper class, middle upper class. That's interesting. So generally, females are people who didn't answer, and the people who, but the p-value here is super low. Not the p-value, the r-squared, excuse me. And the p-value is, I learned how to look at p-value yesterday on this. The p-value is kind of highish. Don't worry about p-value. Another variable we could do, let's go here to relaunch. We'll do one more variable real quick. We could predict someone's gender. Maybe I don't have all the variables I need. Predicting someone's gender. Oh, did it change colors? Oh, because we have prefer not to answer. I was like, why is it green? So high school GPA. Wow, that is a really good indicator. Yeah, I know, Ahood. It's pretty fun, right? There's so many ways of doing this stuff. And high school GPA is a really good indicator of somebody's gender. Why do we have 1,800 observations? Which survey is this? I remember which stat to one survey we have 1,905 observations. Did we combine it? I don't know what's going on. Did Terry randomize it? There we go. And now we have, do you know what a Roth IRA is? So females were likely to say, I don't know what it is. And then we have the yes and the no right here. And you can see the distribution of individuals. And so then we have, wow, that group is really, so this group right here is really female. They're just primarily, does this kind of make a sense of what we're looking at right here, Charlie? I have to go in just a few minutes. And then we go to the leaf report to see inside the leaves. So let me vanish here again. The leaf report is going to show us how many individuals there are in each leaf. So if you go to, this is a very important thing we can do right here. Let me zoom out just a little bit, because when we look at this, I want everyone to always know what we're doing right here. When we do this, let's go ahead and take a screenshot right here. What you should understand about this leaf report is the following. The bars and the splits confuse me a little bit. Oh, so this right here, so hopefully this is the distribution of the y variable. So this is the y variable right here. This is also all the y variable right here. That's the y variable. Does that make sense? Like how to know which one was yes and no? So right here, reading, so I'll hopefully make sense of this. Kind of read what it says up here. And it says these individuals right here had a GPA that was less than 3.64. And these individuals, I believe this is, the red is female. So here's the amount of females, here's the amount of males, and here's the prefer not to answer. So when you look at this, you're looking at the distribution of the Y variable. So these are the people who had a GPA less than 3.64, and that's the distribution of their Y variable. Like they're more male right there. Like that group right there with the lower GPAs is more male. This group right here had GPAs of greater than or equal to this. That's an X value we're using to predict. And this group was more female than male and prefer not to answer. So you can see the female distribution was larger. This is the percent of females. And there was a total of 605. Yep. And so there's 605 people who, and that's the amount of people right here. There's 605 total individuals who meet this criteria. By the time you get down to the bottom, when you look at this group right here, which is very much female, this group right here has 470 people in it, and they have the higher GPAs. They do not know what a Roth IRA is, and they are younger than 20. So there was a total of 605 that, yep. And so does this make sense right here if you go down that these individuals in this group right here meet all these conditions? You have to follow it down. You have to go to here, and you have to say, okay, these individuals had a GPA of 3.64 or greater. They don't know what a Roth IRA is, and their age was less than 20. And then the distribution of the Y variable is what we observe, not that one. The distribution of the Y variable is what we observe right here. This is their Y variable telling us that they are majority female, because the red, if you look up at the top, is, which we don't have it on the graphic right now, but the red, let's click my pen. The red up here, wrong graphic. The red up here is the female. So how do I know these are the females? Because the red up there is female. And then when you get down to the bottom right here, this is just showing you the inside of each of these leaves. So the inside of each of these leaves, can you number the boxes for the leaves? Yeah, that's exactly what we should do. I'm going to do one step further. Watch this. I'm going to grab all the output. I'm going to number it all. Great question there, Charlie. Excellent work. 1,000 points on Hoot and Charlie. Good to see you both here. It was a very slow start. You should watch the beginning of office hours. I was trying to get some stuff to work, and I was failing miserably at it. Everyone has an off day. I have an off day once a month. And it's the beginning of this month. No. Actually, I'm going to grab that predict gender thing. All right, cool. We want to see what we're predicting. Okay. So there is our decision tree. And let's number it. And let's go back to here. Click. There we go. Okay. And there we go. Okay, so what you want to do is number this as 1. Let's see, that's not going to show up as well. 1, 2, 3, 4. So which of these has the fewest observations in it? Which of these has the fewest observations in it? 1, 2, 3, or 4? And they're not trying to trick you by, they're not going to put more into, they're equally distributed, the dots across the areas they're in. So 1, 2, 3, or 4, 2. When you go down to here, take a look. You can see that 2 has the least amount of observations because 1, 2, 3, 4. 2, like you said, has the least amount of observations in it. So you can also see the distribution of the Y variable right here, which this is the exact same thing as looking at this right here. So that's the exact same thing as when you're looking at down here in number 2. It just showed you like a miniature version of that. So this is like a miniature version of what you're viewing up there. Now down here, you have the same sort of output. You have leaf 1, right here, 1, 2, 3, 4. 1, 2, 3, 4. So if you're looking at leaf 2, you can tell the observations in leaf 2. You can also read the conditions for it, and you can see how many total there are. So there's only one. This right here is one individual. That is this one individual right here. I got confused where there's a lot split in a lot of boxes. I don't know which one. Yeah, does this make sense right here? You always go to the terminal leaves. Does this make sense, Charlie, right here? Hopefully this makes a little more sense of it. And you look at the probabilities of leaf 2 right here. Here's the probabilities associated with it. This one does, yeah. And it just takes practice. The more you look at them, you're like, oh, this is this leaf. This is associated with this. And numbering it. Yeah, we try not to do big ones, but kind of looking through, you can see how this one's more red. Leaf 3 is more red. See how leaf 3 is more red right here, and the red is going to be the females. So if you look at leaf 3, you can see there's more females in the leaf than males. So here's leaf 3 right here, and leaf 3 had more females. You can see that right there, the more females, and that's leaf 3 right here. With this is 396 females, 72 males, and 2 prefer not to answer. Think that's got it. Does any other questions? I guess the last thing to do is interpret the R squared, which we don't have on the screen. The R squared is going to be the percent of variation in Y explained by the variation in X. So 10% of the variation in the variables in the tree, 10% of the variation in R squared, 10% of the variation in gender is explained by the variables in the tree. 10% of the variation in gender is explained by the variables in the tree. I think that's got it. I'll appear on the screen. I'm going to hop over to a Zoom meeting. But good work, Charlie. I'm going to post a video a little later going over this, so definitely check it out. The video will be out for hopefully people use it this weekend to review and understand decision trees. I might try to make it like a 15-minute review of decision trees and go through the output, like a mini lecture. Live. Oh, we should do a live premiere. Let's do a live premiere. I'll do a live premiere after the Kahoot. So I'll do the Kahoot tonight, and then I'll set the live premiere. We might just do one Kahoot later tonight. It's a crazy week. So we could probably do, let's do the live premiere. Thank you, Charlie, for showing up to those. I haven't done as many of those, and I really appreciate it. So stay tuned. I'll put the live premiere up. I'll be working on that video between doing stuff. I think I can get it done. We'll hope. We'll hope. It's, yeah, awesome. Well, I will let everybody go. And I guess oh man, I hope you're doing all right. Yeah, Charlie, I'll be thinking about you, man. I hope you're doing all right. That is a crazy week. So stay strong, stay strong. Be thinking about you and hoping everything goes well. So Vols help Vols. Keep strong, man. It was negative, so all we're good. Oh man. So glad to hear that. Keep safe and keep strong. Glad to hear that. That's good news. That really makes me feel good there. Quote 3, Vols help Vols. Is that Vols help Vols? Oh, Mutebot's not on. Give me 2 seconds. I'm so sorry. I'm so sorry. It was so quiet and so dead that I was like, wait, I forgot to turn on Mutebot. Mutebot is awakening. Mutebot is awakening right here. So I wish it had a thing that it turned on when I streamed, but I actually made it auto turn on now. So, okay. Sorry that you didn't get points for me. Wait, Charlie, I can add points on. I'm going to add 100 points to your currency, Charlie. So here we go. I am finding you right now, Charlie. I found you, Charlie. I'm editing your points. And let me add a Hoot 100 points. I think we'll just do one big Kahoot. Kahoot, I'm adding points. I'm gonna try to get that video out. I've added both of you 100 points. And so we might just do one big Kahoot. So I might just say one Kahoot today. Because usually it takes me a while to write the Kahoots, and I've got the meetings and stuff, and I've got the video to put out. So I'm like, oh no, because I want to make sure the video's out. So we might just do one Kahoot. But so I'm hoping we get, and so for 201 especially, it's really important for them. I have to leave in 1 minute literally, because theirs will have content questions from the Canvas content quizzes. So thank you so much, Ahood. Thank you, Charlie. I've added 100 points onto both of you. Mutebot is here. Mutebot is here to tell us. Vols help Vols. You've already said yes, Mutebot. Well, that's got it. I got to head off to the meeting. Let me do the quick outro. Bye, everybody. Bye.